Winter has come to Quebec. It was beautiful last week, you saw. It was so wonderful that there were sun flares in my iPhone's camera. But this week, it's chilly, some might even say cold, and there's snow on the ground. Well, when winter comes to Quebec, how do you stay warm? 3 things: wool socks, warm underwear, and science. Back to Making Sense. Well, as I mentioned, we've had a really busy week in the past week. Our subscriptions have shot through the roof. We're going to be taking a look at that. We also have a quick repair job for a sewing machine from Helios Makerspace, and really exciting news regarding a visit to another YouTube channel, actually 2 YouTube channels in one location. They are Pierre's Garage and Phil's Projects, 2 excellent local machinist YouTube creator types who do fantastic work, including the creation of the amazing hammers that they have donated to the What's in Your Toolbox giveaway. I had a chance to try out one of those and even to appear in the background of one of their videos stealing one of these hammers. Unfortunately, that was all an act, so I don't actually have one of these hammers, but let me tell you, in the hand they are really seriously nice. The wooden handle has great indexing. You can just flip around one head to the other. The heads are interchangeable, so they come with brass and Delrin ones, but they can be replaced with hardened steel ones and a peening tip as well. Really cool stuff. On Wednesday, I'm going slightly out of chronological order here, I was in my volunteer shift at Helios Makerspace, and one of the other fantastic volunteers there, Stephanie, was working on a sewing machine that was beginning to act up, and one that had been donated to the space, and she was doing various tune-ups on it. And she showed me a bobbin holder for thread that was having trouble because it had some surface rust issues. And so I said that I would be able to fix that up. She said that one of the other volunteers, Jeff, had suggested electrolysis, but I decided to first go for a simple, basically mechanical way of fixing the problem. I loosened up the rust with a bit of WD and a bit of brushing, a little bit of fine sandpaper. And that was quite effective at removing the rust. Then when I was done, I put on some silicone spray to help discourage future corrosion. So that has been returned to the space today. My partner Deanne is doing a workshop on safety in the wood shop, and she's going to be she's in the process of teaching that right now. So I'm looking forward to hearing how that went. On Tuesday, I went out to the south shore of the St. Lawrence River near Mont-Saint-Hilaire to visit Pierre Baudely, and also Philippe Desjardins was there, and their surly subtitler. Yeah, that's what we'll call it. And yeah, it was a great visit, a lot of fun. These are some seriously silly guys, and we had an excellent time. Shot a video there, and we talked about the life of the YouTube creator, and gave me some good tips for building a channel. I will definitely take your advice. Thank you, Pierre. Thank you, Phil. It's great stuff. Also, Phil gave me a ride back to the island where I live. Anyway, while we were there, they let me in on a very secret project they have, and it involved Well, they need to get a piece of metal to ring at a certain pitch. And so they asked me if I had any idea how to go about this. And with my background in engineering and physics, I had a pretty decent idea that I would be able to do this. And so we're going to go over the process of designing essentially a tuning fork. How do you get it so a piece of metal will vibrate at a specific frequency? So, all right, there we have it. Let's roll. So how do you go about determining how something will vibrate? What frequency will it work at? A common way is to have a vibrating string as an example, where you have a certain length, you can figure out the speed with which the waves will transmit through it, and from that you can calculate the harmonic frequencies. It's possible to do this with steel, but since the speed of sound in steel is 15 times faster than the speed of sound in air, you need a really big piece of steel to vibrate at an audible frequency, whereas you could get, if you wanted middle C on a flute, it would be, you could get a tube about yay long doing it, but you would need something 15 times longer in steel just to hit it and to get a ring. That's why, when Keith Fenner dings one of his shafts, you get a nice high pitch, even though it's a big long piece of steel, because the vibration is very, very fast. Okay, that's one way of doing it, but you need a big, big, big piece of steel for it. Another option is to employ the tuning fork principle, where you have two tines on the fork, which, due to their elastic properties and their moment of inertia, will vibrate at a certain frequency, which is governed by a known equation. So given that, and given the properties of the material that you're working with, you can figure out what dimensions will work to get a certain pitch. Okay, now what material are we using? I'm assuming 1045 steel because Pierre has a lot of that and it's cheap. And so that was the material I looked up. Now we're going to get into the equation for the governance of a tuning fork. Okay, now we're going to get scientific. So we have this equation here, which is the governing equation for a tuning fork. The frequency that you will observe is this magic number, which I'll explain in a minute, divided by 2 pi times the length squared, multiplied by the square root of the Young's modulus times the moment of inertia of the section divided by the density of the material and the cross-sectional area. Now, a few descriptions. Length is the length of the tines. The magic number here has to do with the trigonometry. We'll say it is the smallest solution of a hyperbolic cosine blah 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 blah. Okay, treat it as a magic number now. 1.875 squared. E, Young's modulus, is basically the springiness of the material. If you have, if you were to imagine you have a stiff spring and a squishy, very squishy spring, then the squishy spring will have a lower Young's modulus than the stiff spring. And you can consider a block of metal, or of any material indeed, to be an extra stiff spring. So you have a steel rod. If you put pressure on it or you pull on it hard, its length will change ever so slightly. And so the Young's modulus is a measure of how springy the material is before it hits its yield point and bends permanently. The moment of inertia has to do with the shape of the material and its distribution in space. So let's say you had two pieces of material with equal area, and one of them was shaped like that, okay, that, and one of them was shaped like that. Has an I-beam shape. So we're going to declare that the areas across these are equal, but this one has the material stretched out to the extreme ends in two flanges with a web in the middle. It's an I-beam. If you were to subject these to bending forces like this, to load them along their length, they're long columns, this one, which has a small moment of inertia, is going to bend more than this one, which has the large moment of inertia, because its material is spread out across the top and bottom edges. If you load a horizontal beam so it goes into bending, the upper flange will be in compression, the bottom edge will be in tension, and this way the bulk of the material is capturing more of the stresses, and so this has a stronger bending resistance than that. And that's why moment of inertia, which is initially related to an object's resistance to rotational forces, that's what it has to do with structural strength. Okie dokie. So then, anyway, we got this function. There's the definition for the various parts, and we should make a note that for steel, the Young's modulus is 2 by 10 to the 11 pascals. That's 200 gigapascals, and that's pretty much independent of the type of steel you use. It's an engineering value which is just basically taken as a given. The density of steel is also 7,870 kilograms per cubic meter, or 7.8 tons per cubic meter, which is why it's heavier than water. Water is 1 ton per cubic meter. So with this information, we can now go in and solve for the dimensions of the object. Now, the problem is we've got a few unknowns. We don't know what size the width or the thickness of the tines are, and we also don't know what the length is. So we can get a relationship between them from this, but we can't get any definitive answer. So what do? We just pick out of the air. So I decided that the tuning fork would be 1/2 inch wide, and that it would have 1/4 inch thick tines spaced 1/4 of an inch apart. And that will set, of course, both the cross-sectional area of the tines, and because it is setting the distance of the center line of the tine from the center line of the fork, it also determines the moment of inertia. So that way we have I, we have A, we have rho and E from the properties of steel. We can rearrange, we have the frequency we're looking for, so we can rearrange the equation so the length is the square root of 1.875 squared over 2 pi times the frequency times the square root of this stuff. So all of this under a square root, and we can find the positive root of that, and we will find a length. Now, the best way to do this is with a computer program, and here it is. Okay, now we're back after lunch, and it's a bit gloomier out, so we have to turn on the light. Anyhow, so here's the code. Looking at it, I can see that maybe there's a mistake in there. So, since peer review is an essential part of science, if you see what the problem is with this code, write a comment, and we'll mention anyone who finds out what that is next week. I'm going to do some further analysis. Okie doke. Now, as for what this is for, I could tell you that, but then I'd have to kill you, and that would involve tracking down a lot of people and a lot of travel and stuff like that, so I'm just going to keep that a secret. I promised you some other predictions of the future, and last week when I made my announcement of my 1 dozen subscriptions, and where's that card? Where's that card? I can't find the card. When I made my announcement of 1 dozen subscribers, well, it was just a start. This week we have 23 subscribers. We had 13 actually last week. We have 23 subscribers this week. So I began thinking, well, clearly, we have a trend here. What happens if this trend continues? And so I wrote another Python script. Here it is, part 1. And here is part 2. As you can see, this is completely solid statistical analysis. It just looks at the change in those two over 1 week and calculates forward, if this trend continues, how long will it take for me to reach 100,000 subscribers, 1 million subscribers, and for my subscription base to exceed the population of the Earth? And the answer is, in 35 weeks, every man, woman, and child on Earth will be subscribed to Making Sense. So anyone who's subscribed now, you can feel proud that you're amongst the very first. Anyone who's not subscribed, get in now while there's still a chance. Anyway, that's it for this week, and take care all, and I'll see you soon. And that is Making Sense.